Alright, so I imagine some of you are still struggling with how to put electrons in orbitals and represent that using the electron configuration and orbital diagrams. So I'm going to make this video to try to help you out a little bit. So kind of a recap of what we did in the mini lessons on Thursday and Friday. So, electrons are funny. Electrons are small enough that classic physics doesn't apply to them, so they can have a wave nature when they want to have a wave nature and a particle nature when they want to have a particle nature. And because of that, we can't know exactly where electrons are in an atom. Instead, we have these areas of probability that we call orbitals. So, we place electrons in orbitals. Which are areas of probability where we think we can find the electron. So it's an area of probability where an electron is most likely to be found. There are 4 principal orbitals. And they are the S, the P, the D, and the F. And each orbital has its own unique shape. And can hold a certain amount of electrons. So, we need to know what these things look like. What do they do? What are they used for? Let me grab my eraser. So the simplest orbital that we have, the first orbital, is the S orbital. And S orbitals look like spheres. S orbitals are the simplest because they are the smallest. There's only one S orbital per energy level. And it can hold 2 electrons. It doesn't matter what energy level we're looking at, S orbitals will only ever hold 2 electrons. So after the S, we have the P. P orbitals look like dumbbells. And then there are 3 P orbitals per energy level. And they go along the 3 axes of the 3 dimensions, x, y, and z. So this would be your x, your y, and your z. Each p orbital can hold 2 electrons. Which means that p orbitals hold a total of 6 electrons. So we have 3 p orbitals, and each one holds 2 electrons. Because there's 3 of these p orbitals, the p orbitals hold 6 electrons. Next we have the d orbital. I'm not going to be able to draw all of them, but I'll draw one just to show you what it looks like. It's kind of a double clover. There are 5 d orbitals per energy level. Each orbital holds 2 electrons, which gives us a total of 10 electrons per, 10 electrons total in a d orbital. So imagine 5 of these clover thingies all arranged 3-dimensionally in space. Each one of those d orbitals can hold 2 electrons. There's a total of 5 of them, so we say the d holds 10 electrons. 5 times 2 is 10. And last but certainly not least, are the f orbitals. And these ones are even more complicated. They kind of look like flowers. Once again, I can't draw all of them. We have 7 f orbitals per energy level. And then each one holds 2 electrons, which gives us a total of 14 electrons in f orbital. So those totals that I'm talking about, the total number of electrons, that's per energy level. The 4f orbital can hold 14 electrons. The 5f orbital can hold 14 electrons. There are 7 individual orbitals. Each individual orbital can hold 2 electrons. If we have 7 of them all together, we add them all together to get 14 total electrons. So that's what it looks like. That's where electrons are most likely to be found, are in these orbitals. So, let's talk about placing electrons in orbitals. We have 2 methods to show that. The first one is what we call electron configuration. So, when we're doing electron configuration, the key here is that electrons go in the lowest energy level can't spell level first. Which is why the periodic table that I gave you is broken up the way that it is. It's broken up into your blocks, and it's broken up into energy levels. An energy level equals the period number. Except d orbitals, subtract 1, and f orbitals, subtract 2. So for d, it's going to be period number -1. And for f, it's going to be period number -2 to get the energy level. So, there are two methods to placing electrons where they belong. All of them first involve you knowing the total number of electrons. So you get that from the periodic table. Then you've got two methods. You can use your periodic table and keep counting across. Each period also has next to it the orbital that you're dealing with. So for hydrogen and helium, you'll see a 1s next to hydrogen. Hydrogen and helium, both of their electrons go in the 1s orbital. If you go to something more complicated like iron, you'll see a 3d orbital in it. So you have to go and fill all of the orbitals before iron using your periodic table. So you start at hydrogen, do hydrogen and helium at 1s, and then go down to lithium, lithium beryllium at 2s, and so on and so forth until you get to 3d and how many ever iron is. I think it's 6 in. So that's one way to do it. The other way to do it is you can use this handy dandy diagram if you want to recreate it. So, the way that this diagram works is we draw arrows diagonally through it. And you follow the path of the arrows to place your electrons. So you'd start 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. You follow the arrows diagonally to place your electrons. You got to remember how many electrons fit in each type of orbital. So remember, s is 1 electron, p is 6 electrons, s is not 1 electron, it's 2 electrons, d is 10 electrons, and f is 14 electrons. So you put your first 2 electrons in 1s, then you put your next 2 electrons in 2s, you put your next 6 electrons in 2p, your next 2 electrons in 3s, and so on and so forth, until you got to wherever it is that you were going to. So, let me do an example out for you, and we'll do iron out as an example. Iron. Iron's atomic number is 26. So I have 26 electrons that I need to place. So I'm going to use this chart to help me. I know I have my first 2 electrons in the 1s. Then I go to the 2s for my next 2 electrons. So I'm down from 26 electrons to 22 electrons I still have to place. After 1s and 2s comes 2p. So there's my 2p, and it's got 6 electrons. So now I'm down from 22 to 16. After 2p comes 3s. And another 2 electrons, so now I'm down to 14. After 3s comes 3p. And 6 electrons can fit in the p orbital, so that brings me up to 8 now. After the 3p comes 4s. Put 2 electrons there, that brings me down to 6. After the 4s comes 3d. And I can fit all 6 of my electrons in the d orbital because I can hold a maximum of 10. So the electron configuration for iron: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. You can use this for any element on the periodic table and it'll work, or you can use the other method of looking at your periodic table and counting across until you get to the orbital that you're in. So that's how electron configuration works. The next thing we got to look at are orbital diagrams. Orbital diagrams show electrons in the same energy level only. We use arrows, up and down arrows. Arrows are going to represent your electrons, boxes represent your orbitals. So for S we have 1 box because there's only 1 orbital. For P we have 3 boxes because there's 3 orbitals. For D, we have 5 boxes for 5 orbitals. And for F, we have 7 boxes because there are 7 orbitals. Each box can hold 2 electrons, but they don't pair up until they have to. So each box can hold up to 2 electrons, and electrons don't share boxes until they're forced, until they have no other option. So let's look at the orbital diagram for iron, since I used iron for its electron dot diagram. Or not its electron dot diagram, its electron arrangement. So erase all this. So for iron, we only need to show the electrons that are in its outermost energy level, or its uppermost energy level. In this case, that is energy level 4. And for iron, in energy level 4, it has a 4s orbital and a 3d orbital. So we're going to draw one box and label it 4s. And we're going to draw 5 boxes and label it 3d, because those are the 2 orbitals that we need. This shows us all of the electrons that are on the same energy level. So 4s is lower than 3d, so I put my first 2 electrons in the 4s box. And they have opposite spins. The electrons have opposite spins, so we put opposite facing arrows. Then I count over 1, 2, 3, 4, 5, 6. So if I look at my periodic table, I count over 1, 2, 3, 4, 5, 6, and I run to iron in the 3d orbital. That tells me I have 6 electrons that I need to place. These electrons aren't going to share until they're forced to. So there's 1, 2, 3, 4, 5, and then my 6th one's going to share. So that would be the orbital diagram for iron. Alright, I'm going to do one more out, and this one's going to involve some F elements. So I'm going to choose lead. So lead is in the 6th energy level, so I need to show all the electrons that are in that 6th energy level. So I'm going to have a box over here for 6s. And if I look at my periodic table, after 6s, you might think you want to go to 5d. But if you notice there's a little cross there, that means to jump down to the other little cross, down to the lanthanides. So after the 6s comes 4f. So I need to draw 7 boxes for that. Then I can jump up to the 5d. And I'm going to end with 6p. So, since lead is in 6p, I'm going to look and see that there are 2 electrons in the 6p orbital. So I place my 2 electrons in 6p, and that means all the other orbitals before it are full. So I need to place all of my electrons in these boxes now. So that would be the orbital diagram for lead. Today in class, you're going to be working more on practicing electron configurations and orbital diagrams. I'm around. I'll have the chat up. I'll have a Google Meet during scheduled time if you have questions. We can solve out some more of these problems if you have questions about that or about the previous assignment that we did on Thursday and Friday. So, good luck on this dreary day. Stay healthy. Stay safe. See you later.